Hello everyone. Today, I'd like to talk about the law of conservation of energy. First of all, what exactly is energy? This is a basic physics question that most high school students already know the answer to. But if we travel back 200 years, around the year 1800, and ask a physicist this same question, what is energy? He would probably feel very confused. Because back then, people didn't use the word energy at all. Instead, they used words like vis viva, tension, and natural forces to describe related physical phenomena. In fact, the concept of energy went through a very long historical evolution. It didn't gradually mature until around 1850. The word energy itself comes from Greek, which means inactivity. Aristotle once used this word to represent actuality and activity, and its meaning was totally different from what we understand in modern physics today. Before the mid-19th century, scientists relied on terms such as vis viva, force, and motive power to discuss the physical phenomena that we now define as energy. It was only after the law of conservation of energy was formally established that the term energy gained its precise and modern scientific meaning. The origin of the law of conservation of energy is closely linked to human exploration of the essence of heat. Back in the 18th century, the caloric theory was the mainstream view in physics. People thought heat was not a type of motion, but a real fluid-like tiny particle. Antoine Lavoisier gave this particle the name caloric. This hypothetical caloric had three main characteristics. First, it flowed just like water. If you put a hot iron ball into cold water, caloric would flow from the hotter object to the colder one, until their temperatures finally balanced out. Second, caloric took up physical space. That's why objects expand after being heated. Caloric particles slip into the gaps between molecules, and push these molecules further away from each other. Third, caloric had no measurable weight. Even though it could generate powerful force, it remained weightless, just like an intangible ghost. In his famous book Elements of Chemistry, Lavoisier classified caloric as one basic chemical element, together with oxygen, nitrogen, and hydrogen. The caloric theory quickly gained wide acceptance. At that time, it could reasonably explain and predict many physical phenomena. It worked perfectly to interpret latent heat. For example, ice soaks up heat while melting, yet its temperature stays unchanged. Scientists explained this phenomenon this way: caloric particles blend with ice molecules, and turn into an unseen combined state. People held the idea that heat could never be lost or newly produced. It only shifts from one object to another, never comes out of nowhere, and never vanishes completely. Nevertheless, this materialized definition of heat limited people's cognition of energy conversion. If heat was a kind of substance called caloric, while mechanical work belonged to physical movement, the two would be totally separate in nature. People could hardly figure out how they could convert into one another. Although the caloric theory sounded perfect, it still showed obvious flaws in real industrial practice and extreme experimental conditions. In 1798, Benjamin Thompson, also known as Count Rumford, was in charge of cannon barrel drilling work at the Munich arsenal. During his work, he noticed a very common phenomenon: friction generates heat. Based on the caloric theory, people believed the heat produced by drilling metal came from this logic. When metal was ground into powder, its ability to store caloric decreased, so the caloric inside was squeezed out and released as heat. To verify this, Rumford used an extremely dull drill bit that could not produce any metal shavings at all. He then put the drill in water and kept rotating it continuously. The result was surprising. The water actually boiled in just 2.5 hours. Rumford then made a sarcastic comment. He said if heat was truly a kind of fluid stored inside metals, then continuous drilling could produce endless heat. That would mean the cannon barrel contained an inexhaustible amount of this caloric substance, which was impossible. In his research paper, he wrote that any isolated object which can provide an endless supply of something cannot be a material substance. Rumford realized that only motion could be generated infinitely. This conclusion directly ruled heat out of the category of chemical substances, and brought it back to the field of dynamics. 1 year later, in 1799, the 21-year-old scientific genius Humphrey Davy conducted a more precise and rigorous experiment. He used clockwork devices to make two pieces of ice rub against each other inside a vacuum container, and the whole experiment was carried out below freezing point. According to the caloric theory, the melting of ice requires a large amount of caloric. However, in a low-temperature vacuum environment, caloric could neither be obtained from the air nor conducted from the outside environment. But surprisingly, the ice still melted through friction. Davy drew a clear and powerful conclusion: the essence of heat is the vibration of microscopic particles. Under the strictest experimental conditions, he proved that mechanical work could directly create heat without relying on any material medium. From today's perspective, these two experiments were decisive and groundbreaking. Yet back then, they were ignored by the scientific community for decades. Why did such important findings get neglected? The reason is simple. Although Rumford and Davy successfully disproved the caloric theory, they failed to put forward a quantitative formula. They could not explain the core question: how much mechanical motion corresponds to how much heat energy? They only pried open a tiny crack in the old theory, but did not completely push open the door to the truth. After all, scientific progress is never achieved overnight. Humanity still had to grope forward in the dark for nearly half a century to complete the exploration of heat and energy conversion. It was not until 1824 that a breakthrough finally arrived. At that time, steam engines roared across the globe, and the Industrial Revolution was completely reshaping the world. Even so, engineers back then built and improved steam engines just like ancient humans drilling wood to make fire, relying entirely on experience and luck. They constantly argued over trivial technical problems: which worked better, steam or alcohol? Should they use higher pressure or lower pressure? And none of them could find a definite answer. Then came a game-changer, a 28-year-old Frenchman, a military veteran and a talented young engineer named Sadi Carnot. In his only published work, Reflections on the Motive Power of Fire, he abandoned those endless trivial technical debates, and raised an ultimate question for thermodynamics: what is the fundamental limit of heat engines in generating power? At Carnot's time, the caloric theory was still the absolute authoritative theory, and Carnot himself also believed in this theory. Based on caloric theory, he put forward a brilliant analogy: the waterfall of heat. He compared the working principle of heat engines to water wheels. Just as a water wheel generates power when water falls from a high place to a low place, Carnot believed that heat engines work because caloric flows from a high-temperature heat source to a low-temperature condenser. With this hypothesis, he designed a perfect and ideal heat engine with no friction and full reversibility, and proposed the world-famous Carnot cycle. Through rigorous logical reasoning, he came up with a conclusion that shocked all engineers of his time, yet revealed profound truth. The maximum efficiency of a heat engine has nothing to do with its working medium, no matter it is water, alcohol, or air. Its efficiency limit only depends on two physical values: the temperature of the high-temperature heat source, and the temperature of the low-temperature condenser. This conclusion set an insurmountable ceiling for the Industrial Revolution. Simply put, temperature difference creates power, and the greater the temperature difference, the higher the engine efficiency. But no heat engine can ever convert heat into work with 100% efficiency. Carnot was undoubtedly a genius, and he single-handedly laid the foundational framework for thermodynamics. Ironically, his groundbreaking work received almost no attention at that time, with only 600 copies printed in total. Tragically, Carnot passed away young in a cholera outbreak in 1832 at the age of 36. Due to the fear of contagion, people burned all his personal belongings, clothes, and most of his manuscripts, leaving only a small number of diaries preserved. Decades later, when scientists sorted through these surviving notes, they were utterly shocked. They found that in his later years, Carnot had completely overturned the caloric theory, the very theory he once relied on to build his research. He clearly wrote in his notes that heat is not matter, but a form of motion. Even more astonishingly, through rough calculations, he had already figured out the equivalence relationship between heat and mechanical work, nearly 20 years before Mayer and Joule officially published their relevant discoveries. Carnot was like a lonely prophet standing on the peak of science. He used a flawed theory, the caloric theory, to deduce the absolutely correct and monumental Carnot theorem. And before his death, he had already achieved the key theoretical leap toward the law of conservation of energy in his mind, yet he never got the chance to share this great discovery with the world. It was not until the 1840s that Clausius and Lord Kelvin continued Carnot's research on the Carnot cycle and rebuilt the complete theoretical system of thermodynamics. They abandoned the wrong part of the caloric theory, retained Carnot's core ideas about temperature difference doing work and thermodynamic irreversibility, and finally established the second law of thermodynamics. In this sense, Carnot is not only the intellectual predecessor of the fathers of thermodynamics, but also the loneliest founder of the entire modern physics system. In the 19th century, the world of physics viewed the various forces of nature, such as heat, light, electricity, and magnetism, as separate and independent kingdoms, each ruling its own distinct domain. Back then, physicists relied on a range of fluid theories. Heat had its caloric fluid, electricity had its electrical fluid, and magnetism had its magnetic fluid. These forces were thought to be entirely distinct and never interfere with one another. Everything changed in 1820, when Danish scientist Hans Christian Ørsted made an accidental discovery. He found that an electrified wire could deflect a nearby compass needle, which perfectly proved that electricity could produce magnetism. This groundbreaking discovery shocked the whole of Europe, completely shattering the long-standing barriers between these isolated fields of physics. Meanwhile, there was an Englishman named Michael Faraday. He started his career as an apprentice bookbinder and barely knew any calculus. Despite his limited academic background, he trusted his scientific intuition and proposed a reverse line of thinking. He believed that nature is fundamentally symmetrical and harmonious. So if electricity could generate magnetism, magnetism should also be able to generate electricity. He even solemnly wrote down a goal in his daily diary: convert magnetism into electricity. To accomplish this ambitious goal, Faraday devoted 11 long years to relentless experimentation in his laboratory. In 1831, he attempted to place the strongest magnet he could find next to a wire, hoping to induce an electric current in the wire. Yet he failed repeatedly. A static magnetic field was just like a stagnant pond, producing no effect on the wire at all. It was not until August 29, 1831, that Faraday designed a sophisticated and clever experimental device. He wound insulated copper coils on both sides of a soft iron ring. Coil A was connected to a battery, while coil B was connected to a galvanometer. Here came the first miraculous experimental finding. He observed that when coil A was kept continuously electrified, coil B showed absolutely no response. However, in the brief instant of connecting or disconnecting the power supply to coil A, the galvanometer needle connected to coil B jerked violently. This brought him a crucial revelation: motion was the key to the whole process. Faraday then conducted another experiment, sharply thrusting a magnet into a closed coil, and once again, an electric current was successfully generated. He finally had a complete epiphany. Magnetism alone could not produce electricity out of nothing. To generate electric current, we need a changing magnetic field, or mechanical motion that cuts through magnetic lines of force. This remarkable phenomenon is what we now know as electromagnetic induction. Technologically, this landmark discovery gave birth to humanity's very first electric generator. But its significance in the history of philosophy and human thought was far more profound than merely powering a few light bulbs. Faraday did not merely reverse the experimental logic of his predecessors. More importantly, he fully demonstrated the interchangeability of different natural forces. The mechanical work of shaking a magnet by hand could be converted into electric current, namely electrical energy. Then the electric current passing through a wire resistor would generate heat and light, transforming into thermal energy and light energy. For the first time in human history, Faraday's experiments clearly revealed a revolutionary truth to the world. There were no isolated electrical fluids or caloric fluids in the universe at all. Mechanical force, electricity, magnetism, and heat are essentially just different manifestations of the same ultimate physical reality. They are much like currencies from different countries. As long as they follow specific conversion rules, such as electromagnetic induction, these forms of energy can be freely converted into one another. This groundbreaking proto-energy theory sent huge shockwaves throughout the global physics community. It provided an irrefutable and pivotal experimental foundation for the later core concept of the interconversion and conservation of energy. Although no one could provide a precise definition of energy at the time, a number of brilliant minds spanning optics, electromagnetism, and even physiology had already begun, almost simultaneously, to employ a novel intellectual tool in their reasoning. And this tool was protoenergetics. These boundary breakers stopped debating whether heat was a material substance, and instead began to take for granted that an indestructible motive force exists in nature. First, in the field of optics, when Fresnel was deriving the wave theory of light, he keenly realized that the reflection and refraction of light at the interface of different media must adhere to a certain balance of activity. Otherwise, light would simply vanish into nothingness. Then, in electrochemistry, Faraday firmly believed that the electric energy produced by the voltaic pile, that is, the battery, was by no means created out of void. He rejected the mysticism of electricity generated merely by contact, and asserted that electrical energy must come from some kind of force consumed in chemical reactions. Finally, in the life sciences, the German chemist Liebig even applied rigorous analytical thinking to living organisms. He proposed that an animal's body heat and physical strength essentially come from the combustion, or oxidation, of food inside the body, which releases a certain form of force. The formal law of conservation of energy had not yet been born at this stage, but its core methodology had already taken the first solid step. Scientists across different disciplines were all exploring the same fundamental question. If different forces can be transformed into one another, must there be something that remains eternally conserved throughout the entire transformation process? During the decade from 1840 to 1850, experimental evidence had sufficiently matured, and the law of energy conservation was officially established. This groundbreaking progress was achieved almost simultaneously and independently by 4 scientists from different European countries. The first of them was a German physician named Julius Robert Mayer. In 1840, aboard a ship bound for Java, the 26-year-old Mayer performed bloodletting on an ill sailor and observed a special phenomenon. He found that the blood in the veins of sailors in tropical regions was as bright red as arterial blood. This seemingly trivial detail to others kept lingering in Mayer's mind. Eventually, he figured out the truth. In high-temperature environments, the human body does not need to burn much food to maintain body heat, so the oxygen in the blood will not be fully consumed. From this, he concluded that food, body heat, and human physical activity are essentially the transformation of the same energy within the organism, and physical work and heat are equivalent. In 1842, Mayer published a paper titled Remarks on the Forces of Inorganic Nature in Liebig's Annalen der Chemie und Pharmacie. In this paper, he first explicitly stated the universal law of energy conservation and roughly calculated the mechanical equivalent of heat based on the specific heat capacity data of gases. This marked the first time in human history that the principle of energy conservation was publicly presented in written form. However, the academic circles at that time had extremely rigid barriers. As merely an amateur physician, Mayer's paper lacked complex reasoning, and was filled with obscure philosophical terms and biological analogies. In the eyes of orthodox physicists back then, he was just like an ancient alchemist spouting nonsense. Mayer suffered far more than collective academic cold shouldering. He endured even crueler blows in his life. Soon after, 2 of his children passed away one after another. To make matters worse, the publication of Joule's research and other scientists' works triggered a years-long academic battle over the priority of the energy conservation law. Struck by these successive setbacks, this talented scientist suffered a severe mental breakdown. In deep despair, he once jumped from a third-floor window. Though his suicide attempt failed, it left him with lifelong physical disabilities, and he was later confined to a mental institution for a long time. It was not until the 1860s, when the law of energy conservation became a fundamental cornerstone of physics, that people rediscovered Mayer's contributions from dusty old publications, just like unearthing precious historical relics. In 1885, the science historian Düring hailed Mayer as the Galileo of the 19th century. If Mayer was the theoretical pioneer of the law of conservation of energy, then James Joule was its experimental founder. Joule was born in 1818 in Manchester. He came from a family of brewers and was not a professional scientist, but a brewer. In 1838, at just 20 years old, while working in the family brewery, he developed an interest in improving electric motors. He then began a series of experiments that lasted over a decade, and the results were truly astounding. He adopted multiple independent experimental methods, including using falling weights to drive paddles stirring water, heating through electrical resistance, compressing pistons, and utilizing friction between blocks, to precisely measure the quantitative relationship between mechanical work and heat generation. He was extremely rigorous and meticulous in his research, capable of detecting temperature differences as small as 1/200th of a Fahrenheit degree. On August 21, 1843, at the meeting of the British Association for the Advancement of Science in Cork, Joule stood before an audience of only 5 people and presented his paper titled On the Calorific Effects of Magnetoelectricity and the Mechanical Value of Heat. He reported a mechanical equivalent of 838 foot-pounds and solemnly wrote in the postscript, "The grand agents of nature are, by the Creator's fiat, indestructible. Wherever mechanical force is expended, an exact equivalent of heat is always obtained." Just like Carnot and Mayer, Joule's experimental results were widely questioned at that time. In 1845, the paper he submitted was rejected by the Royal Society. Faced with widespread skepticism, Joule did not break down like Mayer. Instead, he chose to return to the laboratory and kept conducting his water-stirring experiments with persistent dedication. In 1847, at another meeting of the British Association for the Advancement of Science in Oxford, Joule presented his increasingly mature research findings. According to his later recollection, this presentation almost went unnoticed again, were it not for a young man who stood up. That young man was William Thomson, later widely known as Lord Kelvin. Years later, Lord Kelvin recalled that he was profoundly impressed by Joule's paper and described this experience as one of the most valuable memories of my life. With the support of Lord Kelvin and the recommendation of Faraday, Joule's paper on the mechanical equivalent of heat was submitted to the Royal Society through Faraday in 1849 and published in Philosophical Transactions the following year. His final measured mechanical equivalent was 772.24 foot-pounds, approximately equal to 4.155 joules per calorie, a value strikingly close to the officially accepted standard today. If Mayer relied on medical intuition, and Joule was driven by experimental obsession, then the driving force behind Colding's pursuit of the conservation of energy was the grand vision of Nordic natural philosophy and his profound religious faith. Colding came from a farming family and once worked as a carpenter's apprentice. His life witnessed a crucial turning point when he met Hans Christian Ørsted, a Danish scientific giant who had earned widespread fame across Europe for his discovery of the electromagnetic effect. In 1840, at the Scandinavian Scientists' Conference, Colding intended to present his theoretical findings. However, the rigorous Ørsted stopped him, warning him that pure philosophical speculation was worthless in the field of physics without solid experimental data to back it up. To verify his unique insight, Colding designed and conducted a series of rigorous mechanical experiments in Copenhagen. He repeatedly dragged sleds loaded with heavy cannonballs across tracks made of brass, zinc, iron, and wood, precisely measuring the heat produced by friction, as well as the proportional relationship between the sled's travel distance and load weight. His experimental results not only confirmed the universality of heat generation through friction, but also enabled him to calculate the accurate value of the mechanical equivalent of heat from the collected data. What makes Colding's research particularly unique is that he integrated natural philosophy with his theological beliefs. As early as 1840, he put forward a forward-thinking inference: the various forces of nature are manifestations of the Creator's essence, and therefore indestructible in the universe. At that time, he named this theory the principle of the indestructibility of natural forces. In November 1843, the very same year Joule first presented his relevant paper in England, Colding submitted his groundbreaking paper to the Royal Danish Academy of Sciences in Copenhagen. Titled Some Theses on Force, this work unfortunately fell victim to an unfair historical fate, just like the research experiences of Carnot, Mayer, and Joule. The review committee of the Danish Academy considered his ideas too advanced and overly speculative, so they refused to publish the paper immediately. Only a short summary of his research was kept in internal institutional records, and the full text was not officially released until 1856, 13 years after its submission. There were two key reasons for the neglect of Colding's research. First, all of his work was written in Danish, while the European scientific community at that time was dominated by English, French and German academic languages. It was just like hiding a precious scientific secret on a remote, isolated island. His paper was not translated into English and published in the Philosophical Magazine until 1864. By that time, Joule, Mayer, and Helmholtz had already been widely recognized and shared full credit for the discovery of the law of conservation of energy. Facing this situation, Colding gave up competing for research priority, but he never yielded or stopped exploring. Instead, he applied the core concept of energy conservation to practical engineering fields. He served as the chief national engineer of Copenhagen, personally designing and planning the city's modern water supply system and underground pipeline network. He even applied thermodynamic principles to conduct in-depth research on storm surges in the Baltic Sea. Today, in modern scientific history research, especially in English-language academic literature, Colding's academic status is being comprehensively re-evaluated and recognized. Historians have now reached a general consensus. During the intellectual boom of the 1840s, the law of conservation of energy was independently discovered by four outstanding scientists. They are Mayer, Joule, Helmholtz, and the Danish scholar who completed those unique sled experiments in the Nordic tundra, Colding. Helmholtz was born in Potsdam in 1821. He was a German doctor and physiologist, and later became one of the most erudite scientists of the 19th century. Similar to Mayer, Helmholtz's breakthrough also centered on animal heat. At that time, however, a theory called vitalism prevailed in the field of physiology. This theory claimed that there was a supernatural life force existing in all living organisms, and Helmholtz was deeply skeptical of this view. In 1845, in his report on the theory of animal heat, he showed extremely calm rationality. He asserted that there was no magic in any life process, and that muscle strength and body temperature came entirely from the chemical energy released by food combustion. He also acutely pointed out that mechanical energy, electrical energy, and chemical energy are essentially equivalents of the same energy under different forms and standards. Later, his core ideas were further sublimated. On July 23, 1847, the 26-year-old Helmholtz delivered a groundbreaking paper at the Berlin Physical Society, a paper that rewrote the history of physics, titled On the Conservation of Force. In this influential work, he displayed master-level mathematical logic and accomplished three historic achievements that have been etched into scientific history. First, he achieved logical closure. He combined the ancient intuition that it is impossible to create a perpetual motion machine of the first kind with the central force model in Newtonian mechanics, and proved that if we admit perpetual motion machines do not exist, the conservation of energy is an inevitable deduction of Newtonian mechanics. Second, he made clear conceptual clarification. He strictly distinguished between tension and living force. The former is what we now call potential energy, and the latter refers to kinetic energy. Meanwhile, he put forward the mathematical analytical formula for the mutual transformation of these two forms of energy. Third, he completed a systematic hierarchical construction. He established a complete hierarchical structure ranging from general theoretical hypotheses to specific physical phenomena, including heat, electricity, magnetism, and chemical changes. This crucial improvement turned the conservation of energy from an isolated physical formula into a supreme rule that governs all physical fields. Different from Mayer's writing, which was full of philosophical overtones and a little obscure, Helmholtz's expression was based on mathematics and rigorous to the point of cold precision. Even so, this forward-looking and transcendent idea was initially rejected by traditional old-school physicists, who dismissed it as nothing more than tedious philosophical deduction. Yet the power of truth is irresistible. With the continuous development of electromagnetism and thermodynamics, scientists were shocked to find that all new discoveries in these fields perfectly fell within the theoretical framework preset by Helmholtz decades earlier. It is worth mentioning that as early as 1840, a Russian chemist named Hess put forward Hess's law. The law states that in any chemical reaction, the total thermal effect remains consistent, whether the reaction is completed in one single step or through multiple steps. Essentially, this is an independent discovery of a special form of energy conservation in the field of chemistry, and Hess's law laid a solid foundation for the future development of thermochemistry in physical chemistry. Joule's speech at the 1847 Oxford Conference deeply impressed 23-year-old Lord Kelvin. This important encounter motivated Kelvin to systematically study Joule's papers on the mutual transformation of heat and work. Around 1850, Rudolf Clausius and Kelvin independently established the basic framework of thermodynamics, and clearly differentiated the first law of thermodynamics, which refers to the conservation of total energy, from the second law of thermodynamics. In 1850, Clausius released his first paper on thermodynamics, which is recognized as the first document that clearly elaborates on the mechanical theory of heat. In this paper, he introduced the concept of U, also known as internal energy, transforming energy conservation from a philosophical principle into an operable mathematical formula. In 1851, Kelvin published on the dynamical equivalent of heat. He successfully reconciled the seemingly contradictory viewpoints held by Joule and Carnot and achieved a theoretical synthesis. Joule believed that energy could be transformed but would dissipate, while Carnot argued that heat would be lost. Kelvin offered a crucial insight: although energy may be irrecoverably lost for human use, it is never destroyed in the physical world. This thought marked the initial formation of the second law of thermodynamics, and it also represented a major upgrade in scientists' understanding of energy conservation. People's cognition of energy thus evolved from simple conservation to a deeper understanding of the coexistence of conservation and dissipation.
Since its emergence in the 19th century, the conservation of energy has long been regarded as an empirical summary. Scientists have conducted countless experiments and found that energy seems to never disappear. However, this was initially just treated as a statistical law. It's just like how we observe 1 million white swans, and then conclude that swans are probably white. So here comes the question, why must energy be conserved? In 1915, German mathematician Emmy Noether, whom Einstein praised as the greatest female mathematical genius of all time, published a groundbreaking achievement that completely rewrote the underlying logic of physics. This is Noether's theorem, which states that behind every conservation law lies a hidden symmetry. Popularly speaking, the so-called symmetry means invariance under a certain transformation. Take a sphere as an example. No matter how you rotate it, it always looks exactly the same, and this is what we call rotational symmetry. According to the corollary of Noether's theorem, the conservation of energy essentially exists because the laws of physics possess time translation symmetry. That is to say, the laws of physics never change with the passage of time. If you measure the gravitational constant as g in the laboratory today, the measurement result will still be g tomorrow, next year, and even 100 billion years later. As long as the evolution law of a physical system stays consistent and smooth on the time axis, there must be a physical quantity in this system that remains numerically unchanged forever, and this constant quantity is what we define as energy. From this perspective, the conservation of energy no longer needs tedious experimental verification. As long as we believe the universe operates with consistent logic across time, energy conservation becomes an absolute logical necessity. It is no longer a random coincidence of physical experiments, but an inherent geometric truth of the universe. We can find similar corresponding laws in physics. The conservation of momentum corresponds to spatial translation symmetry, which means the laws of physics are identical in Beijing, on Mars, and anywhere in the universe. The conservation of angular momentum corresponds to spatial rotational symmetry, meaning the laws of physics work the same in all spatial directions. And the conservation of energy corresponds to time translation symmetry, ensuring the laws of physics remain consistent at all times. Looking back from the perspective of the 21st century, the stable and predictable world we live in entirely relies on the elegant symmetry inherent in time and space. Even if the universe eventually moves towards heat death, and all stars burn out and go dark, this rule of conservation will persist forever as long as time flows smoothly. The conservation of energy is the firmest promise the universe leaves us amid all drastic cosmic changes. The establishment of the law of conservation of energy is not merely a great victory for physics, but also a profound ideological revolution, which has laid an important foundation for the philosophy of Neo-Kantianism.